Hello, my name is Dr. Jonathon Speed. I am the Product and Applications Manager at Keit Spectrometers, and it is my delight to talk to you about the development of a robust spectrometer for online and real-time monitoring of oil quality. I've included my email address on this slide, and it appears again at the back, along with my phone number. If there are any questions that come up throughout the course of this presentation, or you'd like to contact me for any more information, please do reach out, feel free. I am more than happy to receive your call or email. I'm also easy to find on LinkedIn, so please do reach out. The obligatory introduction slide. Keit Spectrometers, who are we? We are originally a government spin-out. So we were formed when the government Space Research Centre near Oxford in the UK developed a spectrometer designed to go to the Martian atmosphere. And the intention was that it would sample the atmosphere and perform infrared measurements there to analyze the gases that were present. The problem is, if you want to get a spectrometer to go to the Martian atmosphere, you need it to survive launch. It needs to be small, it needs to be compact, it needs to be reliable, and it needs to survive absolutely every element of getting it there. Once it was designed, the government decided that actually this is something we could probably spin out as a company. If it survives that kind of treatment and it can launch and it's reliable, probably worth putting on Earth. And that's when Keit was born. So we are still based on the same site, but we're now on the commercial side of that research site in our shiny new building, purpose-built specifically to allow us to produce spectrometers and train them on new applications. Our spectrometer is based on static optics. I will go into a little bit more detail on that in a minute, but effectively it means that we have no moving parts. This means that you can mount it anywhere, near pumps, near forklift trucks, near people where people move around. You can hit it with a hammer and it doesn't really care. Compared to laboratory instruments, for example, which if you mount them anywhere near vibration, will literally vibrate themselves to pieces and stop working. So, our product. It's 30 centimeters long, 24 centimeters wide. It has an armored shell and a sensing probe at one end. And we thought to ourselves, what else is a bit like that? Sensing probe, armored shell, similar sizes, an armadillo. And it's integral in the infrared industry to have a pun based on IR. So we are the IRmadillo, which is I think he's quite cool. And he's got a little bit of attitude as well. And that is the product that we. So how does it work? I did say I would talk about static optics. So this is the obligatory physics slide with mirrors. The light is created in our emitter and it shines onto the end of the probe. Some of the light actually extends out of the probe by a method that's called attenuated total reflection. So this is a physics and chemistry effect. The light extends out around about 2 microns through the window into the sample itself. You may remember this from undergraduate chemistry. This means that the light then interacts with the sample, but ends up back inside our probe again. The light then goes down the end of the probe and hits this this beam splitter. A beam splitter allows half the light to go through and reflects half the light as well. You've probably seen this effect yourself. If you've ever looked at a window, and you've been able to see outside of the window, but also been able to see your reflection at the same time. This is really common if you're falling asleep on a train with your head against the window, that kind of thing. Then that's a beam splitter. And in this case, half the light, let's say the yellow track, is reflected off the beam splitter and goes anti-clockwise around this track. The other half of the light goes straight through and goes clockwise around this track. And we combine the two phases of light on this detector array, and they are ever so slightly offset, and that's what gives us a interference pattern. This is very similar to Young's slits, you may remember from school physics, I think it is, as when that gets introduced, but this creates an interference pattern. We then do something called a Fourier transform on that. That's where the FT in FTIR comes from, and that produces a spectrum. And the spectrum is what contains the information that we use. So all of the development in our company has led to developing a smaller arrangement of mirrors that's robust, that's reliable, that are mounted together on a single piece of metal. What this means is if the spectrometer is to vibrate because it's mounted near a pump or there's just natural vibration in the area where it's installed, everything vibrates together. All of the mirrors move as one, the beam splitter moves as one, which means that the light doesn't notice the vibration because everything's moving as one single monolith. for want of a better word. Traditional instruments make use of moving mirrors. Now, the moving mirrors have to run across a very well-defined track, and if there is any vibration or movement at all, it can create a loss of signal and a loss of interferogram, and the spectrometer stops working. So that's why static optics are absolutely critical to taking FTIR spectroscopy out of the laboratory and online into meaningful industrial relevant locations. So how do you use spectroscopy for monitoring a process? The first thing we do is we acquire a calibration spectrum. So we take our calibration spectra either from a specific sample set, that is something like a design of experiment methodology where we make up known concentration values, or we piggyback on a process that exists. A classic one we use a lot is fermentations. They're run in batches traditionally. They're very easy to dial into 3 or 4 batteries, and by the end of that, you've got enough spectra for a calibration. For edible oils, what we've done previously is we've actually installed online and we've just allowed the natural variation to be captured, especially when if the process goes outside of specification, has to be brought back into spec. That's fantastic for building a calibration because we see a wide range of concentration values. We then use that concentration coupled with some form of offline analysis technique. So for design of experiments, we knew what that was to start with because we made up specific samples. For piggyback processes, we have to use some kind of extractive technique, for example, HPLC, chemical assays, which can include things like titrations. So for free fatty acids, a titration is good enough. We can use that to get our calibration data. We then build a model. So we can either create a univariate model, which is very simple peak height tracking, or a chemometric model, where we interpret the entire spectrum in one go, and we read that like a fingerprint or a barcode. And we have lots of these fingerprints overlaid on top of each other, and computational models can pull that out to give us concentration values. Then the last thing is to validate that model. You don't want to upload a model and not check it's working. You do that with anything, even with a pH probe. You put it through buffers and you check that the calibration is right. We do the same thing. So once installed online, we take some reference samples every now and then just to check that things are how they should be. And if they're not, it's very easy to put it right. But that very rarely happens. The only time that can happen is if you have a natural product that comes in through the front door that has a very big change to what it normally has outside of normal specifications. Now, the beautiful thing about spectroscopy is it can detect that things are drifting outside of its calibration and tell you so that you can do something about it. Now, you may be sat there thinking, hang on a minute, I've heard all of this. We tried infrared in the past and it didn't work. We spent a lot of money on it, we spent a lot of effort on it, and it gave us nothing. Chances are that was near infrared. Near infrared was going to be the solution to everybody's problems 10, 15, 20 years ago, and unfortunately it has failed to deliver. Now, near infrared is similar to mid-infrared and FTIR, but there are some fundamental differences. Firstly, near infrared probably had a fiber optic cable with a probe on the end of it coming into your process. Near infrared fibers are really easy to make. They're very easy to string into fibers, into actual cables and probes. Mid-infrared probes based on fibers are atrocious. They're incredibly fragile. They have a very low light throughput, and that means that they are not really suitable for industry, which is why we don't have one. We have a solid light pipe. Near infrared also tells a fundamentally different piece of information to mid-infrared. Now, we can use the entire electromagnetic spectrum for spectroscopy, and that gives us different bits of information depending on what we're looking at. So ultraviolet and visible light, commonly called UV-Vis, looks at the excitation of electrons from their ground state, which is here, up to their excited state, which is up here. So that is a single rung on the electron ladder, effectively. And that gives us things like color and ultraviolet. So if you look at the structure of carotene, which is a molecule in carrots, you'll notice there's lots and lots of electrons flying around in that, and they can all be excited very easily. And that's why carrots are very, very brightly colored. Another obvious example is chlorophyll. Chlorophyll, bright green, and that's because the magnesium ion inside it has a lot of electrons that can fly around into the molecule itself, and that gives us our bright color. So this is the kind of technology you might want to use to look at things like color and strongly absorbing in the electronic part of the spectrum, such as chlorophyll. Mid-infrared is a similar thing, but at the vibrational level. So this is a smaller level, much smaller energy, and that's why infrared is lower in energy than in UV invisible. But again, it's a single rung on that ladder from the ground up to the excited. Near infrared jumps a few rungs in one go. It might jump 2, it might jump 3, it might jump 4, and not always from the ground state. That makes near infrared much, much harder to understand what's going on because they are not fundamental vibrations, which is what this ground state to excited state means. Fundamental vibrations, fundamental transitions are very easy to interpret. Any chemist fresh out of university or college can look at a spectrum from a mid-infrared instrument and give you some idea of what's going on. It takes an utter genius and expert to interpret a near-infrared spectrum by looking at it. I certainly can't do it, and I'm not sure of anyone who can read a near-infrared spectrum completely apropos of nothing and tell you what's going on. So the level of information is completely different. I mean, in real life, what it means is that trying to differentiate between similar molecules, such as FFAs in oil, the difference between mono, di, and triglycerides, the difference between phospholipids, using near infrared is extremely difficult. And you need very large calibration sets. It's a lot of effort, a lot of money, and not necessarily going to give you any reward. And that is the problem a lot of people fell into. With mid-infrared, it's much, much easier. Much, much, much easier to build these calibrations. You need much fewer samples, and you can get a lot more information out. An example, with near-infrared, this picture, we only can see the silhouette, which is kind of a comparison of the resolution that near-infrared gives you. Is it a vase or is it two faces? We can see that this might be someone looking at someone else, or we may have a lovely a vase here. With mid-infrared, we see everything. And at that point, we can clearly see it's a vase. We have that third dimension, that perception of depth. We can see absolutely everything and we understand. That's the kind of difference in information that you get with mid-infrared compared to near-infrared. And if you need that information because your technology, your application is difficult, such as edible oil refining online, that's where that information is so useful. So a few examples to show you the kind of data that we've managed to pull out using this static optics spectrometer. The first one is qualitative. So this is a principal component analysis scores plot. What this shows us are features within the spectra, and this can go to lots of different dimensions. I've only done two-dimensional plot because it's easy to see. So we can see different types of oil have been clearly separated. We have soybean oil down here. We have olive oil, canola oil, soybean mix, canola oil, soy and soybean mix, pure canola oil up here. Over here we have various states of adulterated olive oil with soybean. Here we have the pure olive oil, and then we have this line here of adulterated olive oil with canola oil in it. Down here we have very low amounts of canola oil in the adulteration. Up here we have more. The point here is that we can see very clear clustering. The spectrometer can look at an oil and it can tell you what type it is. Now, that's probably not necessarily too useful in a day-to-day. You know what type of seeds you're putting in, you know what type of oil you're making. But if you want to be able to check that online, you can do that with a spectrometer. But more importantly, you can start looking at things like high and low oleic blends. That's the kind of information we can pull out. And we're doing some work, as I currently speak, identifying different types of triglycerides, and we have a 100% success rating in pulling out 24 different types of triglyceride and identifying them individually. So qualitative measurements with the IRmadillo are very, very easy to do. And you can do those at the same time as a quantitative measurement with one instrument. It's all about how we interpret the spectra. We can interpret it in different ways and pull out a lot of information at once. Here's some quantitative results. These were done in our laboratory. What we did is we took sunflower oil and we did a design of experiment where we dissolved different amounts of free fatty acid and fatty acid methyl ester. I can go into much more detail on a one-on-one call with someone to talk about this. We also have an application note published about this work as well. We then created a calibration using partial least squares methodology, and that's the chemometric calibration I was talking about earlier. What that does is allows us to quantify the different amounts of acids and the different amount of esters that are present in the mixture. Now we can pull out individual, so we can say how much linoleic acid is present, how much oleic acid, how much linolenic acid is present. We can do all of that. For the ease of use for this particular application, we've lumped everything together as total free fatty acid, because that's what you would want to use for example, controlling your caustic dosing, your lye, your sodium hydroxide, to make sure that you're dosing the right amount in. Now, the next stage of this is actually converting this to amount of sodium hydroxide required, because weight percent of free fatty acid is vaguely useful, but it's more useful to know how much of the carboxylic acid moiety itself, how much neutralization is required, because the greasy tail isn't as useful as knowing how much chemical needs to add. And we can see fatty acid methyl esters as well, and we can pull them out individually, and we can look at everything. We can do online quality analysis in real time. The average error across the spectrum, or across the concentration range, sorry, for the FFA is 0.24%, and the average error for the FAME is 0.06%. Now that's over that concentration range, running from 0 to 0.32, I think it is, and from 0 to 1.6. There's a little bit of statistics that goes into that, so depending on the concentration range we look at, the average error is slightly different, but we know we can get high-performing calibrations, and you can see from this plot that we have our reference value on the x-axis and our measured value on the y-axis. Ideally, we'd have a straight line with an r² of 1, and that is pretty much what we've got. It's all well and good doing things in the laboratory, but getting out on plant into an oil refinery itself is orders of magnitude better. That gives us real data from the process itself. It shows whether we work in real conditions with different oil types as well. So these are results that we have from a refinery we've been working with. We've been installed right at the end of the process, just before bottling, because it was the easiest place to install the instrument, quite frankly, for their proof of concept trial. Off of these results, they are now moving the instrument dramatically further upstream of the chemical dosing, because they're actually going to use results for feed-forward algorithms to calculate how much neutralization to do of the free fatty acids in real time. So they are delighted with these results, and we're delighted they're moving the instrument to be used in real time for chemical control. So these results were taken from an online installation and sampling that was taken offline throughout that installation and verified in the laboratory. And we've managed to get an average error of 0.083% for free fatty acid. You'll notice these are much lower values than 1.6, and that's why the errors come down. We've also looked at chlorophyll for them, and we've managed to build a calibration curve of 0.75 ppm, which I think is fantastic. And that we'll show in a second, allows us to monitor things like chlorophyll spikes. I'm not sure that's sufficient to do process control for the chlorophyll, but certainly good enough for monitoring spikes of chlorophyll that may come in through the process and alerting the operators to do something about it. So these are the results from the long time install. The instrument was installed in the middle of February and left through to the middle of March in this location. What I think is particularly interesting is this spike here. So the customer wants to run at 0.1% free fatty acid. That is their specification. That's very clear that they are achieving that for the vast majority of the time. However, there are clear moments where they're not able to achieve that. And at this point, we can see a different batch of oil came in. It had a higher amount of free fatty acid, and they were under neutralizing with their caustic dosing. And it took 12 hours before it was noticed. And that was noticed with regular sampling that were taken offline as they would normally have been. And at that point they noticed, and of course they corrected. And they overcorrected. And as a result, this means their product may be out of specification and they may have to throw it away. And this means they're using more caustic dosing, more chemical than they need to, and it's costing them more money. And it takes 24 hours, give or take, before they are back within specification. With an online install, that would have taken 2 minutes, because you'd notice every single time, and as soon as that spike started to go up and the FFA concentration went up, you can feed forward the correct dosing algorithm to make sure that the chemical concentrations stay where they need to. As for the chlorophyll, so as I alluded to earlier, we can definitely see overall trends the data is a lot noisier, but to be fair, we are less than 1 ppm of chlorophyll, and that is remarkably low concentration to be monitoring spectroscopically. But it does mean that if the concentration were to spike, if something were to fail, we would certainly notice that very, very quickly. So what's next in our pipeline? The next thing we're going to be analysing is phosphoric acid control. So we're trying to look at the metal ion concentration and the difference between hydratable and non-hydratable phospholipids. Infrared spectroscopy doesn't directly see the metal ions, but it can see the effect that having metal ions has on other elements within the spectrum. So, for example, the PO double bond in phospholipids or the CO double bond in the glycerides themselves. And we can also measure properties. So we're currently building a calibration curve for iodine value, and we'll have that published fairly soon, hopefully within the course of the virtual conference. And the question we throw open to you, what would you like to be able to measure? If there is something that you wish you could measure in real time, but you can't yet, please do reach out. I am always happy to run proof of concept feasibility experiments in my laboratory. We can analyze some samples for you free of charge and write that up as a proof of concept. We'd be delighted to do that. And get a conversation going. It's the fastest way of learning. It's the one thing that will be more challenging doing this remotely, but I would love to get a conversation going. And if it feels like it's a conversation we could have multiple people on for a round table, let's do it. So just a quick overview of where we think we could be useful in the process. This is obviously the point that I mentioned earlier at chemical dosing control, but later on as well, downstream of the separator, just allowing feedback control of the separator itself. Is it working optimum concentration? Is it working exactly as it should do? Are we getting all the water out? Is there any residual water? Are we losing acid? You can also put on the outlet of the gums and soap stock to make sure that, sorry, not acid, oil, to make sure that you're not losing oil and losing valuable product in your waste. And also at the very end, this is where the customer installed as a continual quality check at the back end. It's online, it's real time. It means you don't have to worry about doing lot testing and doing individual samples. It's always running continuously, 365 days a year. So our conclusions. We are actually at the point now where closed loop control and real-time process optimization for complicated processes is within reach. And it's by using technologies like the IRmadillo that can enable that. Spectroscopic measurements do allow concentration dosing control, which I find extremely exciting, and it's a fantastic time to be integrating them into your process. And robust FTIR measurements allow for this. They give you the information you need to do things like lye or caustic dosing, and phosphoric acid dosing as well. And as soon as we have those metal ion results, I'll be happy to share those as well. So the static optics of the IRmadillo brings the information of FTIR out of the laboratory and into industrial settings itself. As I said at the beginning, here's my email address, here's my phone number. That is a UK phone number, but hopefully it wouldn't be too expensive. But feel free to reach out by email as well. And I can always phone you if you don't want to phone a UK phone number. But I really do look forward to hearing from you. It's been a delight to give this talk. Thank you very much for listening.